work.
Can you show us how you would solve 3-5 problem 8?
Sure.
I was able to do it after consulting other people, but it took me a while to get.
Show that n factorial is bigger than 2 to the n?
Yeah, so the way I did it was I multiplied each side by n plus 1, so then you get n factorial, but then the right side doesn't exactly simplify, but then I showed that the right side is greater than 2 to the n plus 1, and then use like the law of syllogism, basically.
Okay.
That n plus
That
1
would,
factorial.
that would work great.
You would do it,
so what would I do for this? Yeah, basically, I would say if I multiply this by n plus 1, right? And what's our range on n? Bigger than or equal to 2? So n plus 1.
4, I believe.
Okay, so n plus 1 is definitely bigger than 2. So this is definitely bigger than 2 times 2 to the n. Yeah, that's exactly what I would do. So then n plus 1 factorial is bigger than 2 to the n plus 1.
I just wanted to see if I was missing something.
That's the first way that would occur to me, I think. Because the intuition of n factorial versus 2 to the n, this gets multiplied by 2 each time. This gets multiplied by something bigger than 2, right? That's what's horrible about factorials. The thing you're multiplying by goes up each time. And that's exactly what that observation feeds off of. So yeah, I think that looks really good. Other induction questions?
We can do 3.4 number 1.
.4 number 1. I was hesitant to put that on here because I thought someone might ask me to do it. And I expect it will be messy, but it will probably be similar to how we did other ones like sum of squares or sum of integers. So P of n says this. So let's assume P of n, which means this. And then let's add n plus 1 cubed to each side. And the trick is to somehow turn that into n plus 1 squared times n plus 2 squared over 4. So I'm going to use an entire page for my ignore area. And let's see what happens if we plug n plus 1 into this original formula. And that looks like a mess. As soon as you get a 13 in there, you know you probably did something wrong, but maybe not. So if we could show that that was equal to this, then we might have a hope. So let's just look at this side. And so this will be 4 times n plus 1 cubed. And we can put the divided by 4 all over on the bottom. And so this looks like n to the 4th plus 2n cubed plus n squared plus 4n cubed plus 12n squared plus 12n plus 4 all divided by 4. So n to the 4th plus 6n cubed plus 12, 13n squared plus 12n plus 4 all divided by 4. Close enough. No. So, so I got a 12n. There should be an 8n. Interesting. Say again? Yes. So yeah, 2n cubed plus 8n squared plus 8n. So this is 12n. Thank you. So they will be the same thing. So your trick is to take this expression, right, and expand it into that, and then work to show that that's equal to this thing, right? And then you've got exactly this statement of p of n plus 1. But yeah, that's kind of ugly and error prone. All right, other induction questions or any questions? All right, and I will grade these and get them back to you Wednesday. And we have a quiz coming up Friday, is that correct? So I'm thinking that will probably be on induction or maybe something else, but I'll figure it out before Wednesday and we'll talk about it. Let's talk about counting. So, counting can get us into all kinds of things. We're going to talk about ways that we can enumerate the number of certain things, the number of ways you can do certain things, the number of combinations of certain things in various forms. So I want to start with something called the product rule. And throughout this first part, we're going to be thinking about trying to accomplish some task. So we have something that we want to do, and we want to look at the number of ways in which we can do it. So suppose a procedure P can be done as a succession of two procedures, P1 followed by P2. So we have some procedure we're trying to do, and we can do this by first doing some procedure P1 followed by a second procedure P2. So if P1 can be done N1 different ways, and P2 can be done N2 different ways, then P itself can be done N1 times N2 different ways. So this is called the product rule. So an example, you have 2 people and you have 20 desks. And the procedure you're trying to do is to have these 2 people go into this room and each take a seat at a desk. And they can't both be at the same desk. We want to know how many different ways can that procedure be accomplished. In other words, how many different ways could these 2 people come into a room with 20 desks and sit down? And we can answer that using the product rule by thinking of this procedure as a succession of 2 steps. Procedure P1 is the procedure where the first person picks a desk. And then after that first person has sat down at a desk, we do procedure P2, which is where the second person picks a desk. Right? And the order in which these people choose their desks does not change the number of ways that they can sit. So it's legitimate to break it into the succession of 2 steps. So if procedure 1, just one person goes into a room with 20 desks and chooses a desk to sit at, how many different ways can that be accomplished? Right? Number N1 is equal to 20 because they could sit at desk 1, desk 2, or desk 20. Okay, after that procedure is completed, how many ways can procedure P2 be done? Right, that can only be done 19 ways because there's only 19 desks to choose from. And so N1 times N2 is 380. That's the number of ways 2 people can choose to sit at 20 different desks. Pretty straightforward. But we can use this idea for a lot of different situations. So suppose we're switching to a new student system and we have new student IDs. And the student ID will consist of 2 letters and 3 digits. So how many IDs are possible? Well, we can phrase that as let P be the procedure, pick a student ID, and ask how many ways can we perform this procedure P? How many different ways can we pick a student ID? And we can break it into 5 pieces. P1, pick a letter. P2, pick a letter. P3, pick a digit. P4, pick a digit. P5, pick a digit. And I haven't put any restrictions other than the first thing has to be a letter, the second thing has to be a letter. They could be the same letter, they could be different. Haven't restricted that. So procedure 1, pick a letter. How many ways can you do that? 26 letters. If we're not worried about picking the same letter twice, picking your second letter can also be done 26 ways. Picking a digit, we got 10 options, 10 options, 10 options. So the total number of ways that we can do this is 26 times 26 times 10 times 10 times 10. So that's the number of possible student IDs with that definition of a student ID. If your first letter has to be either T or F, how does this analysis change?
N1 changes to 2.
Yeah, N1 would have to be 2. There's 2 ways you can pick that first letter. It's a T or an F. Everything else stays the same. This is 2 times 26 times 10 times 10 times 10. If you don't allow the same letter to be used for both, then N1 is 26, N2 is just 25. All right, you go into a restaurant and you're going to order the soup and salad item, and there's 3 soups and there's 5 salads, and you get to pick 1 soup and 1 salad. How many different ways can you order your lunch? Yeah, so you can break it into the task of first choose a soup and then choose a salad. The number of ways you can choose a soup is 3, number of ways to choose a salad is 5. Total number of ways to choose a soup and then a salad is 15. So nothing too startling going on. Four-bit strings. Strings comprised of 4 bits. How many 4-bit strings are there if we haven't taken Engineering 250 yet? We can think of a procedure as saying choose 4 bits. And we can break that into 4 sub-procedures. P1, choose bit 0. P2, choose bit 1. P3, choose bit 2. And P4, choose bit 3. Or I'm just arbitrarily numbering them. Bit 0, 1, 2, and 3. So how many ways can we choose what that least significant bit's going to be? All right, there's 2 ways to choose bit 0, 2 ways to choose the next bit, 2 ways to choose the next bit, and 2 ways to choose the most significant bit. So the number of ways to choose all 4 bits is 2 times 2 times 2 times 2. And in general, right, if you have 8 bits, right, which is just 2 to the 8th. So for a k-bit number, there are 2 to the k ways we can choose the bits that make up that number. This is why there are 2 to the k possible k-bit numbers. So suppose f is a Boolean function of 4 variables. How many possible Boolean functions are there? Well, remember, we can identify a function with its truth table, and it's a 1-to-1 mapping. Each truth table corresponds to a function and vice versa. So if we think of f as having inputs a, b, c, d, we can make our usual truth table, and we just found out how many rows there are in this truth table, because this is all the possible combinations of 4 bits. We know this is going to be 2 to the 4th rows in the truth table. And to define a function, all we have to do is specify what the output value is for each possible input combination. In other words, we have to fill in this output column. And so the procedure of defining a function f can be broken into the procedure of defining the value of f in this first row, and the value of f in the second row, and the third row, all the way down to the 15th row. So we can break this into 16 sub-procedures, P1 through P16. And how many ways can we choose a value for that first row's output? Right, just 2. And so the total number of ways we can fill in this column is 2 to the 16th. And this 16 was 2 to the number of variables. So in general, if you have k inputs, you have 2 raised to the 2 to the k possible functions. So that's a 250 formula that we sometimes state without proving. So 4 variables, you got a whole bunch of functions. 8 variables, you got a ridiculous number, 2 to the 256th, which is like 10 to the 80th or so. All right, suppose you have a deck of 52 playing cards, and you're going to shuffle it up, and you want to know how many different orders can that deck be in, where every card is considered unique. How many different ways could you end up with the cards in a deck of 52 cards being arranged? A lot. So choosing an arrangement of 52 cards can be broken into 52 tasks. The first task is choose which card goes on top. So pick the first card. The next task is to pick the second card. And the 52nd task is to pick the last card. So how many ways can we choose the card that's going to go on top? 52, because we can pick any card to be on top. But then to choose the card that goes below that, we can't choose the card we just put on top. There's only 51 cards left. And finally, when we get down to the last card in the deck and we choose which card is going to go on the bottom, we will have only 1 card left. So the number of ways we can do that last procedure is just 1. And so the total number of ways we can do this procedure is just what we call 52 factorial. And that's going to be a pretty common result. We're going to see a lot of factorials pretty soon. All right, let's look at a function f going from a set M to a set N. These are finite sets. The number of elements in M is little m. The number of elements in N is little n. And if this is just an arbitrary function, no requirements on being injective or surjective or anything else, just a well-defined function, the procedure of defining a function from m to n can be thought of as follows. First, pick one element from m and define what f maps that to. Then pick another element from m and define what that maps to. Pick another element from m, define what that maps to. Do that for all the elements in m. If we know what f does to every element in m, we've defined the function. So the procedure of defining this function from m to n is a succession of procedures First choose what M1 maps to, choose what M2 maps to, and so on, until you choose what the mth element of M maps to. And I'm assuming there's an ordering that I've put on the elements of this set. So I can talk about element 1, 2, all the way up through M. And how many different ways could I assign a mapping for this one particular element M1? How many different things could I map it to? Yeah, I could choose to go to any of the elements in my set N. Go to the first element, the second element, the third element. The total number of elements in there is little n, so the number of ways I can do this procedure is n. And the number of ways I can do this second procedure is n. And the number of ways I can do this mth procedure is also n. So the total number of ways I can define function f is n times n, a total of m times. So that's the cardinality of n raised to the cardinality of m. But if I want my function to be injective, which means that different things over here have to map to different things in n, we can't allow two things to map to the same thing in n. So if I want injectivity, well, my first element m1, I can map that to anything in n. But once I map my element m1, my element m2 cannot map to any of the things in n. It can't map to the same thing that m1 mapped to. So here I only have n minus 1 possibilities. n3 will have n minus 2, and so on. And nm will have n minus m minus 1. And so it's the product of these that tells me how many functions I have, which is a smaller number. If we allow leading zeros, how many three-digit numbers are there? Because choosing a three-digit number is choosing the first digit, from which we can pick from 10 different digits, and then choosing the second digit, we can pick from 10 digits, and choose the final digit, and we can pick from 10 digits there. And so we have 1,000 possibilities. And those are the numbers 0, 0, 0 through 999. And there are 1,000 of those. So the universe still works. All right, so let's talk about the sum rule. if a procedure P can be done by either doing P1 or P2, and P1 can be done N1 ways, and P2 can be done N2 ways, then P can be done N1 plus N2 ways. So product rule, we were doing a procedure as a succession of sub-procedures. Sum rule, we're doing a procedure by either doing P1 or P2. And the number of ways to do P is the sum of the ways you can do P1 and P2. So for example, 3 soups, 5 salads, and you're allowed to order soup or salad, but not both. So how many ways can you order lunch? Well, the procedure P of ordering lunch can be accomplished by either P1, which is ordering a soup, or P2, which is ordering a salad. Number of ways you can order a soup is 3. Number of ways you can order a salad is 5. There's a total of 8 possible lunches. So these are most fun when you put them together. Combine sum rules and product rules. So we've got a simplified version. This is C minus minus. And in this language, a variable is a letter or a letter followed by a digit. Actually, that's how old Fortran 4 worked. It was really restricted. So a variable is either a letter or a letter followed by a digit. So how many variables can you have in this language? Well, procedure P is pick a variable. Procedure P1 is pick a variable which is just a letter. Procedure P2 is pick a variable which is a letter plus a digit. So how many ways can we pick a variable that's just a letter? 26. We're just doing uppercase. How many ways can we pick a variable which is a letter followed by a digit? Well, this is a product rule, right? So we can break that down into Q1, pick the letter, and Q2, pick the digit. So to pick a variable which is a letter followed by a digit, that's a succession of tasks. First pick the letter and then pick the digit. So picking the letter we can do 26 ways, picking the digit we can do 10. There's 260 ways to do task P2. And we can get a variable by doing either P1 or P2. So the total number of ways to pick a variable is the sum of those, 286 variables. Making sense? All right, well, we have a sum rule, we have a product rule, we need subtraction. This is sometimes called the principle of inclusion, exclusion. And this is built around this idea from set theory, which says if you want to look at the size of the union of two sets, it's the sum of their sizes minus the size of their overlap. Because when we union, anything that appears in both sets will only appear once in the union, but it will get counted twice if we just add up the size of the sets, so we have to take away the number of things that overlap. So here's an example of this. So how many 8-bit strings start with a 1 or end with a pair of zeros? So 8-bit strings, we want to know how many of them start with a 1 or end with 0, 0. So if a string starts with a 1, it looks like this. And if it ends with a 0, 0, it looks like that. So how many strings fall into this form? A 1 followed by 7 anythings. 2 to the 7th. Right, that's the product rule applied really quickly. 7 procedures, pick the 7 bits. So there's 128 strings that start with a 1. How many strings end with a 0, 0? Right, we've got 6 things to fill in. This is 2 to the 6th, which is 64. But if we add those together, we get too many strings, because some of these things that start with a 1 also end with a 0, 0. And some of these also start with a 1. So we want to know what the overlap is, which is the number of strings that start with a 1 and end with a 0, 0. And how many is that? Right, that's 2 to the 5th, which is 32. So the number of strings is the number of strings in that first form plus the number of strings in the second form minus the overlap, which is 160. That's a fun one. So formally, A1 would be the set of strings that start with a 1, A2 would be the set of strings that end with 0, 0, and we want to know how many things are in the union of that. And it's the number of things in A1 plus the things in A2 minus the things in the overlap, the intersection. All right, let's take a 5-minute break. I gotta go get more paper, and then we'll talk about the pigeonhole principle.
plan to do on Wednesday?
More of this?
So we'll, I've got a lot of questions to ask about problems in the
Okay.
combinatorics chapter.
Combinatorics will not be on the test, though. I don't know if that affects anything.
No, but
The-
I still have a lot
Yeah,
of
yeah.
questions about it.
Okay, yeah, we can talk about that.
The problems, for example, I think I'm pretty good at mathematical induction. I'm not too worried about that. And this combinatorics stuff is not on this exam, but it'll probably be on the final
Mhm.
exam. And combinatorics is something that I'm not as comfortable with as I should be,
Okay.
or will want to be, like to be. And a number of problems in the book that I did. Well, I did most of the problems in 2.1, 2.2, and 2.3. I didn't get to 2.4
Mm-hmm.
over the weekend. There are several problems that I did that I have questions about that are kind of significant for me.
Okay.
Do you want me to wait for those till Wednesday, or can I ask those now?
Are you coming to office hours tomorrow?
I'm gonna try, but I worked on the combinatoric stuff and some calculus and some other stuff over the weekend. And
Okay.
I didn't really do the programming, so I'll go home tonight and try to do programming tonight.
Okay. So I would say
But I knew that
if it's questions on combinatoric stuff that we haven't gone over yet, let's hold off on asking questions in class.
Okay.
And we'll get through more of this today and Wednesday. But yeah, you can always ask questions about it in class. But if it involves stuff we haven't lectured on yet, then I want to sort of hold off on that
So-
in class. But we can still talk about it in office.
Sure, but if you'd rather me wait till the office, I will. But this is product, in a product rule, some rule.
Yeah.
Inclusion, exclusion.
Yeah, questions about that, go for it. Want to ask them right now?
Now, yeah.
Yeah, go for it.
Yeah. Okay, the problem that I was concerned about was, well, okay. 2.3A8. I did that, I understood that. The one before it, you have to do it, or I did it using a Venn diagram for both, but Chapter 2, Section 3, Problem A7, a survey of 90 people, blah, blah, blah.
Ah,
I thought I did, well, I constructed a Venn diagram, but then they didn't give me enough information to fill the Venn diagram out, like they did on 8.
mm-hmm.
But they gave you some information, and it seemed to me like what I did was I created a Venn diagram and put letters in the different places, and then did some algebra.
Mm-hmm.
And the algebra was like, maybe you call it systems of equations with let's see, 7 letters.
Mm-hmm.
B, C, D, E, F, G, H. And I came down with, it seemed really nice. I was able to come up with an answer for the intersection of all three, for joggers, aerobics, and Nautilus. But my answer doesn't make sense. It's too big.
So let's look at question 7 first, because that's a simpler one, but a general principle.
We said it's simpler, but I didn't find it simpler. 8 I did, and it was not difficult for me, but 7.
So 90 people, 47 tennis, and 42 swam. Is that different from your
No,
number 7?
it is different.
Yeah.
Well, forget about that one then for now.
Well, let me talk about this one because it's representative of word problems on these. 90 people, 47 played tennis, 42 swam, 17 participated in both. And the question asks how many participated in neither. And so we can call T the set of people who played tennis, S the set of people who swam. And so if we want to know the number of people who did either tennis or swimming or both, in other words, the number of people in the union, right? Principle of inclusion exclusion says that's this. Right, the number who did tennis plus the number who swam minus the number who did both, which is 47 plus 42 minus 17, which is 72. And so 72 people did either tennis or swimming or both. So the number of people who didn't do any would be the number in the universe minus the number who did any, which is 18. So if you only have two groups you're working with, it's pretty straightforward, right? They all kind of look and feel the same. And it's just variations on that. But when you have more activities, that rule gets more complex. So here's what it looks like for 3 activities. So it's the sum of those minus the pairwise intersections, but then plus the things that are in all 3 sets, because you've subtracted them off one too many times if they fell into 2 of those pairwise intersections. And is that the formula you used for, or you just argued it straight with Venn diagrams?
No, I used that at one point, I think. Yeah, I used that.
Okay, but you got a number that was bigger than the universe?
Yeah, oh, well, not bigger than the universe, but bigger. It said that each thing could, it's talking about, these are all 3 activities, classes, aerobics, jogging, and working out on a Nautilus, and it said 30 people were enrolled in each of the 3 classes. So no one circle could have more, in the Venn diagram, could have more than 33 in it, and I came up with 55 as the intersection of all 3. And my arithmetic and my algebra seems correct, but I'll talk.
Yeah, let's look at that, because I don't have the problem.
Yeah.
Because I think it's a different version, but
Yeah, it's funny that the physical book that I got doesn't have the same
yeah.
columns in it that the PDF file does.
Yeah, we can look at
Yeah, we'll
that.
look at it later on.
Okay, cool. All right, so on to the pigeonhole principle. So let me find a good picture. Yeah, so these are pigeonholes. Right, so it's a box that pigeons roost in. And people use pigeons for sending messages, or used to. Right, because pigeons can be trained to go to certain destinations, and you can put a little piece of paper on their feet and they'll fly with it and carry it somewhere. And so you can send a message across town by pigeon, right? And so you have these boxes that the pigeons roost in, and at most 1 pigeon per box. They don't double up. And so this is where the pigeonhole principle gets its name. So what's the pigeonhole principle say? This is the general pigeonhole principle. Given n containers and n plus 1 objects to be placed in those containers any way that you like, at least 1 container will have 2 or more objects n containers, n plus 1 objects, and you put these objects in the containers, you're guaranteed at least one container will have at least 2 objects in it. And that's pretty obvious, right? Here's 4 buckets. Here's 5 things I'm going to try to put into those buckets. There's no way I can put these into those 4 buckets without one bucket having at least 2 things in it. That's all this principle is saying. And you know, I could put all of those into one bucket, and now I have one bucket with 5 things, and I have some buckets with no things. That's okay. All that this is guaranteeing is that once I place these n plus 1 objects into these n containers, at least one of these containers will have at least 2 things in it. And it's pretty obvious, but it's a really powerful result to be able to use. So for example, assuming the people's names start with uppercase letters from A through Z, in any group of 27 people, at least 2 have the same first initial. So we just started Pigeonhole Principle. Given n containers and n plus 1 objects to be placed in those containers, at least one container will have 2 or more objects. So for example, in a room of 27 people, at least 2 will have the same first initial. And how do we know this? Well, make 26 containers corresponding to the letters A through Z, and place each person into the container corresponding to their first initial. We have 27 people being placed in 26 containers. At least one container will have 2 people in it, and those 2 people will therefore have the same first initial, which is whatever that container corresponds to. Similarly, if you pick 8 people, at least 2 of them were born on the same day of the week. We can place them into one of 7 containers corresponding to the 7 days of the week, and we're guaranteed at least 2 of them will be in the same container, which means they were born on the same day of the week. If you have a 10-point quiz and you have 12 students, at least 2 students must have gotten the same grade as each other. Because a 10-point quiz, your grades can be 0, 1, 2, up through 10. That's 11 possible grades. Put each student into a container corresponding to the numbers 0 through 10, and at least one container will have 2 students. Those 2 students got the same grade. But for such a simple principle, we can get some surprisingly deep results out of this. So here's a claim: every positive integer has some multiple consisting only of zeros and ones. That's a weird thing to claim. So 1, well, that's an integer consisting only of zeros and ones, so that's easy. What about 2? Any multiples of 2 consisting of only zeros and ones?
10.
Yeah, 2 times 5 equals 10. There's our multiple. What about 3?
One, one, one.
1, 1, 1. What's 1, 1, 1 divided by 3?
37.
That works for me. So 3 times 37, yeah, that's right, is 111. I can do 4. I can do 5. How about 6? That's what I was wondering. Yep, 6 times 185. So I mean, it looks like it's holding up for these first few integers, but to me at least, certainly not in a way that makes me ready to say, yes, this works for any integers. There's a multiple of 17,205 that'll look like this. It's not immediately clear, but we can prove this pretty easily with the Pigeonhole Principle. So let's do that. So we're going to work on some number n. We're going to find a multiple of it consisting of only ones and zeros. Okay, so consider the following numbers. 1, 11, 111. And so on, just all of the integers consisting of only ones. Down to this last one, which has n plus 1 ones. So we're just picking n plus 1 integers consisting of only ones. And let's think, modulo n, what each of these is congruent to. All right, how many different things can something be congruent to mod n? There's n things that you can be congruent to, 0 through n minus 1. So we have n possible congruences, and how many numbers are we trying to find here? We're working with a list of n plus 1 numbers. So if we consider containers corresponding to what a number is congruent to modulo n, and we place n plus 1 objects into those n containers, one of those containers has at least 2 things in it. If 2 things are in the same container, it means they're congruent to the same thing modulo n. 2 things that are congruent to the same thing modulo n, their difference is divisible by n. That was our first notion of congruence. So pick 2 of these that are congruent modulo n. Their difference is a multiple of n. And if we choose the difference of the larger one minus the smaller one, it's something with a bunch of ones minus something with a smaller number of ones. That difference will be a bunch of ones followed by a bunch of zeros. And that's guaranteed to be a multiple of n. So we actually showed something a little more powerful. For any integer n, there is a number consisting of some string of ones followed by a string of zeros, which will be a multiple of n. And that's probably not an obvious conclusion. but it's true nonetheless. So let's see what this does for 7. And in fact, most of these were a series of 1s followed by a series of 0s. Let's see what 7 does for us. So 1, 11. So there's our 8 numbers. And we're going to work mod 7. So 1 is congruent to 1, 11 is congruent to 4, 111. Is congruent to 6. (1,111) is congruent to 5. This next one is congruent to 2. And this, well, that's a ripoff. That one's actually a multiple of 7. Doesn't have to end up being that way. This next one is congruent to 1. So I mean, we kind of lucked out in that we found something that was a multiple of 7. But if that hadn't happened, right, we could have worked with this and this. These are both congruent to 1. That would be congruent to 1 minus 1, which is 0. Right, and sure enough, that is a multiple of 7.
You just proved that result, and you said it's not very obvious. Is it a useful result?
Sure. Everything's useful, isn't it? What could that be used for? I don't know. I'm not feeling creative. I suspect it's useful.
I'll accept the general statement,
Okay.
without a specific example.
It's even better when you like come up with results that aren't useful. When I burned out on CS in the 90s, my goal was to get as far from anything applicable as possible. So I went into very abstract mathematics and algebraic geometry, and stumbled into something called mirror symmetry, which turns out to be very applicable because it's a core to like a lot of string theory. But the people doing this didn't realize that at the time. They were just doing pure mathematics, and some physicists found these results and started using them to come up with all kinds of physical results that couldn't be explained mathematically, but were nonetheless verified as being correct, and it became a big mystery.
So I guess you could say any number that's a series of 1s followed by a series of 0s is not prime because of that?
I don't know if that's true of any number. That feels a little stronger. So I'm wondering if there's any primes that are just a succession of 1s, because it can't end in 0 because it would be even. So 11 is a prime, and that could be an anomaly. But we live in 2019, where we can get seed in 1 of succession. That's interesting. I'm guessing there are other primes like that.
Yeah, probably.
If we click on it. Can't type anymore. You're about to break the universe. Wow, that's weird.
You broke the poor guy's website.
Yeah. Huh. I'm seeing a pattern. Yeah, now we broke it. So maybe not other than 11.
Huh. It's probably not what that tells you though anyway, so you don't prove that a different way.
Yeah, yeah. It's an interesting question. All right, so let's look at another unusual application. So given n plus 1 positive integers, less than or equal to 2 times n, at least one divides another. In other words, we cannot find n plus 1 positive integers less than or equal to 2n that are all pairwise relatively prime. In fact, now this just says something more. One will be a multiple of the other. So let's say n equals 5. So we need to find 6 integers between 1 and 10. Where none is a factor of the other. So we clearly can't pick 1 because that's going to divide everything. We could pick 2, but then we can't pick any other even numbers. So we could pick 2, 3, 5, 7, and 9. Well, we're supposed to pick 6, so we don't even have 6 things we can pick. That won't be, right, our 6th number will have to be even, so it'll be a multiple of 2. So we can't pick 2, we could pick 3, 4, 5, we can't pick 6. We could do 7, 8, 10. And 3 doesn't divide any of those, but 4 divides 8 and 5 divides 10. So that doesn't work. And this claim is that no matter how carefully we pick our n plus 1 numbers, at least one will be a factor of another, right? And this is for any n. So if n is 100, we can't pick 101 integers between 1 and 200 without this happening. And if you try to do this, it becomes pretty easy to believe, right? That if we pick numbers that are too small, they just divide too many things. And if we start too far along, we run out of numbers before we get to n plus 1. But it might be a hard thing to prove in general that this works for all n. But again, this will work pretty easily with the pigeonhole principle. I don't know if I can do it in negative 10 seconds. All right, we'll start with this on Wednesday because it's too beautiful to rush through. So we'll start with that, and then we'll talk about combinations and permutations, which will be kind of the heart of this part of the course.